Hi, everybody, and welcome back to CAD for Electronics. This is Cad1133 and Cad2131 for those playing along. And today is our lab number 3, and we're going to talk about something that's very exciting in my opinion, and that is the microprocessor. Okay, so without further ado, let's get into the slide presentation, and we'll go through that, and then our in-class exercise, and then as always we do have a follow-up lab for you to work on in your own time. All right, so the first thing is make sure that you do your quiz today. At some point it is open for the entire day, so some nice easy marks, and it's a way for you to ensure that you are actually getting all the material out of the course that is expected. All right. And as always, the quizzes are open resource. So anything that you can find, the help menu, user pages, your notes, my lectures, they're all free to use. And I just need you to make sure that you understand what I'm asking and show me. Okay. So what is a microcontroller unit? A microcontroller unit is a little bit different than a microprocessor that you would find in a computer, in that it has a series of peripherals. And these peripherals allow us to communicate or sense what's happening in the outside world. It can still do the arithmetic functions that you would see inside a microprocessor, but it has a bunch of extra things that you wouldn't typically see. For example, being able to drive an LCD directly, or have something called a zero cross detect, so that we can tell when to turn on a power device depending on the AC signal. It could have internal amplifiers or comparators. It could have something called CLCs, which are basically an FPGA that's programmable inside your chip. We can do analog to digital conversion, which is something most processors can't do. We can also set up things like clocks and timers, so that events can be measured, and we can also have some internal memory and output things in, say, a pulse width modulation. So if we are looking for to drive a motor, for example, we can sense the motor's position and drive a set of FETs accordingly. Okay, so in essence, the microprocessor in our design is the brain. Okay, and so using our lab number 2, we want to continue on with our lab number 3. All right, and so the first thing that we're going to want to do is to create a second sheet. Okay, why would we want to create multiple sheets in a design? The answer is fairly simple and obvious. It should be obvious that we don't want to crowd our one sheet with too many pieces of information, and we may not have available to us larger sheets like a C or a D size sheet, where we would have ample room to get most designs in. And so this is a way for us to use a conventional printer and start to break down our larger design into sub-circuits. Okay, so we're going to create a new sheet, and we're going to go up here to our design, new root sheet, and as you can see, it opens up a new sheet, and then we can go and we can rename this sheet. There's a couple ways that we can do it. We can go into the sheet properties and rename the sheet here. I'm going to call this MCU 2 for me, because my design's finished. And you'll notice that it actually updates it. And so how do we get back to our original sheet? What you can do is simply right click, and it should show you all of the sheets that you have. And so here we are in MCU2. I can go back to my power supply and so on. Okay, the next thing that we should talk about is our VCC rail, or our main voltage, if you would. Okay, and what we're looking at doing is changing our voltage from the conventional 5-volt TTL to 3.3. And why would we want to do this? Well, later we're going to find that we have some 3.3 volt components, and we want to basically not blow them up. And so let's take a look at how to actually change that. So what we're going to do is, again, we're going to go under Design, Configure Power Rails, and here we have a 5-volt rail. But if we change to our power rails to VCC, you'll notice that we can change literally to 3.3, and it will be attached to voltage collector to collector and voltage drain to drain, so VCC and VDD. Okay. And now if I put in a power and a ground, and we grab a voltmeter here, DC voltmeter, we run our simulation, we get our 3.3 volts, which is perfect. It's exactly what we wanted. Okay, so the next thing that we want to do is we want to actually start to import a bunch of parts. We're looking for our consil 5. We're looking for the jumper. We're looking for the 3 LEDs, so red, green, and yellow. We're looking for a transistor called a ZTX320. And of course, we want our microprocessor, which is a PIC 18F26K22. And so we're going to basically bring all of those parts in and follow along as I assemble it for you. Okay, so the first thing that we want to do is lay out our 3 diodes with 3 series resistors. It's important that you get them in the right place. And so you can see I have RA3 here, A4, and A5. So go ahead and drop in the 3 series resistors, change the value to 100 ohms, and then put in your 3 LEDs. While you're working, I'll continue to talk a little bit here. So RA stands for register A. You'll notice that there's also a register B, and there is a register C that we can't see right now. This becomes important when we start programming our microprocessor, because this is an 8-bit microprocessor. This represents a whole bit, okay? And basically what we're going to be able to do is turn these bits on and off, okay? Next, we have our 3 LEDs, and so these are sourcing. So I'm providing a voltage here. It's going to flow through here, and then we're using this transistor to sync it to ground. So when this transistor turns on, basically the LED will turn on. And so we have 3 resistors here as opposed to 1 down here, so that we could, in theory, turn on 2 or 3 of them at the same time and get the same voltage. Obviously, if I had a single resistor down here, the current across the resistor would change, therefore the voltage would change, and it would not work as intended. Okay, pause the video if you need to. So the next thing is something that gets forgotten all the time. This is basically the programming port. It's very important that we get this correct. Okay, so what we're looking at here specifically is we're connecting PGD and PGC, which is your clock and your data for your programming. Obviously, being able to program a microprocessor is very important. And the super important one is this pull-up, this 10K resistor in here. And you can, if you look at the data sheet, Microchip actually recommends that you put a capacitor in here, a very small capacitor, to make sure that you're not MCLR or not clear, is stable. The downside is that when you go to program it, you need to remove that capacitor. So we're just not going to bother putting it in for now. We have a fairly good power supply, so I'm not worried about it. And so as you're drawing this circuit, we're going to continue to talk here about what what we're looking at. So what does it mean with a not memory clear? Okay. What it means is that as long as this pin is high, so this pin has some voltage on it, the microprocessor will run. If it goes low, so for example, this jumper is closed and it's pulled low, it'll put the processor into reset. So if ever you have a microprocessor that isn't running and it's a new design, the first thing you should look at is the memory clear, hold high, and do I have power to the chip? All right. Again, we have a bypass capacitor here. This is going to want to live as close to the chip as possible. And so that's why I drew it in here. I like to draw mine in very tight with the chips the way I intend them. Quite often you'll see in larger designs, they will have banks of capacitors that are all the decoupling capacitors, and they don't specify which one goes where. For a small design like this, I really like to have the component, in this case C5, living in the same little bit as the chip. All right, again, pause the video if you need some more time. Otherwise, we'll keep moving. Okay, so the next thing here is we're going back to the transistor, and we've attached it to ground, as you can see here, and we've created a terminal. And so I'm going to pop over to Proteus, and I will show you how to create and edit a terminal. Okay, so what I'm going to do is I'm going to go in here to my terminal mode. I'm going to select a default terminal, and I will place it down here. I will then double click on the part. So that's double left click. And I'm going to call this a CCP. And CCP actually stands for something. So CCP refers to the capture and compare. And so if you take a look here on your chip on the C register, there is actually something called CCP2. And so that's the pin that we're going to utilize. And so I've just called it CCP. As long as we have the same label on both ends, it will literally try to connect the two in our simulation and in our PCB layout. Okay, so if you need more time, pause the video, finish up, and then we'll move on. Okay, so on the topic of editing the terminals, there is also the option to use the little pull down here. And the pull down is great because it will allow you to choose existing labels that you've created. Okay, so once you've created CCP, you'll be able to pull down and select that from the list. This is important when you start to get larger designs and there may be a lot of terminals or a lot of wires or a lot of nets, and you don't want to have a typo between one and the other. I've seen where people have put in multiple grounds or multiple sources and spelled them slightly different and then couldn't figure out why they weren't joining. Okay, so something to be aware of. Okay, so your design should look something similar to this, and we're now going to add a program to this. And so what we want to do is you want to, a couple ways to do it. You can double left click on the part, or you can go in and edit properties. And what we're looking to do is modify or select a program file. And so the first thing to do is download the file from DC Connect, the .hex or .bas file. BAS is a basic file, which is nice for students when they're first learning because it's readable, whereas the hex file is directly what the interpreter outputs into the microprocessor. So it's machine code and it's completely unreadable by humans. Normal humans. I guess there are some people that can still read hex code. Funny story, back when I was in school, we had to manually enter that hex code, and I'll show you what it looks like in a second, but we had to manually enter it into the computer. and it was kind of funny because this is how they programmed the computers in the Apollo program. So you would actually enter a memory location and an instruction, and then go to the next memory location and enter an instruction. And I didn't go to school in the 60s, so it's kind of a sort of moment. But anyway, we'll take a look at that later to at least see what the hex code looks like. But to the task at hand, we want to go in here. We want to browse to the file, and I've got mine saved in a directory called Lab3, and simply choose one or the other. I'll choose the hex file. I'll say open, and you can ignore everything down here for right now, and we'll say okay. There we go. And when we press the simulate button, if it works, it's great. And if not, there's some troubleshooting that we can do. So here we go. I'm going to run mine. And it doesn't look like much other than the LEDs come on. But if we take a closer look at it, you'll see that I have mine set up for digital. So I'll flip mine over to analog for right now. And remember that this is going to cause a lot of extra computation. So if your computer at home is having a little bit of trouble doing all the math in the background, it's fine to leave it on digital. But the idea is that we're going to get an idea of what's happening here and with this circuit. And I will take a few minutes and explain what's actually happening here in a moment. Okay. So let's talk about what's actually happening here. And I realize that with the simulation, it's not really showing up very well. And I will link in some other information on PWM for those interested. But basically what we're looking at by pulse width modulation, we're talking about how long the processor's actually pulling that pin high versus the entire clock. And so you can imagine if it's on 100% of the time, it's on, it's maximum. But if it was only on for half the time, the intensity would be half of total, and you could take it all the way down to completely off. And so for things like LEDs or heaters or even DC motors, you can basically run a PWM signal into it, and it will adjust the speed or the heat or the light intensity. And it's a way for us to use a digital signal to create an analog response. Okay, so let's take a look at what's going on here with our simulation. So I'm going to grab our terminal, and we'll just pop it over here so that we can actually look at what's happening with our signal. So here we are. I'm going to run it and set you to DC. And we'll set this one to basically to ground. These guys can get turned off. And so you can see that what's happening, although it's hard to see it, the program is varying the signal so that it would get brighter. And it's kind of disappointing that we don't get to see it here with our simulator, but I have one better. I will show you the actual board running this PWM program. All right. Okay, so what we're looking at here is actually the first year variant of the board finished, and I flashed it with the program. And what I have here for my screen capture is it's a piece of software from Agilent for an analog discovery. And if you ever find one of these on eBay or Craigslist or something that's relatively inexpensive, I highly recommend picking one up. They're great to do low voltage and low speed stuff. But basically, what we're looking at here is as the light flashes, and I've got the board on a kind of a strange angle, so you can kind of see what's happening better with the LEDs. But you can see that the LED is getting brighter, and what's happening is when it's basically turning on, it's turning on very very quickly and then turning off. And as time goes on, it's on for a longer period of time until it's completely on for a set amount of time. So if I just go into single mode here, then we can stop it and zoom in. And aside from the noise, you can see that it's actually reasonable at creating this sort of uh, dimming effect. And so think of this as your typical traffic light, but with dimming control. All right, and so that's what we've created, and this is what we really wanted Proteus to show us. But if it's not working 100% on your computer, trust me that it works in real life. All right. Okay, I'll get you to go back to your power supply schematic, and we want to add a couple things. In basically, what we're looking at doing is adding these jumpers, this J2 and J3 for me, and we're going to connect it to our power and our ground. And the reason that we'd want to do this is to isolate our power supply from the rest of the circuit. And especially when you're first getting started, or you have a questionable power supply, you might want to put in one of these jumpers so that you can power it up, make sure that your power is good, and then power the rest of the circuit. It also means that you could remove these jumpers and apply a different voltage, which is very useful for things like a development board. Okay, so the next thing that I want you to do is down at the bottom, you'll see this. There will be PSU or MCU or processor or whatever page you happen to be on, and I'll get you to click on it, and it will open up the Design Explorer. And the Design Explorer is a super powerful tool, and we need to be careful with this because we can mess things up pretty badly if we're not careful. And one of the things that I want to show you is basically that we can type in a value. For example, here we know that LED in caps is a part. We used it previously. But you can see here that I'm actually just grabbing the component and dragging it down. Now, word of caution is that you can do this. You can make a huge mistake here where you grab that LED and you pull it down too far. So you end up getting multiple LEDs on things like the capacitor, which would be bad. But then it's very important once you've moved this footprint is that you apply the changes. Okay. And so if you do make a mistake, if I go down here by accident and I make all of these LED, you can discard the changes. Okay. So super powerful tool. All right. Once you have your two LEDs put into position, we can move on to the next slide here, which is to start to modify our PCB layout from last week. All right. And so the first thing that we want to do is we want to change the layer. Okay, so down here, when we highlight and edit properties, the board edge, we want to actually change the layer. We want to change the layer to silkscreen in this case. Typically, my students create a board edge in silkscreen, and so when they go to create their PCB layout, like the next steps, they can't actually create a ground plane or a 3D view or anything, and that's because they don't have a board edge. So you can, today we're taking a board edge and converting it to silkscreen. you can do the opposite. You can take a silk screen, if you've laid it in by accident, and change it over to board edge. Okay. Yeah, go ahead and create a new board edge, however, that is 90 millimeters by 50 millimeters. So up in this corner will be your 0, and we're going to go over 90 and down 50. All right. And it should look similar to this. And then what we want to do is we want to delete all the traces from the PSU section by selecting track mode. So here's my entire PCB, and I want to get rid of all of these tracks. And so what I'm going to do is there's a couple ways to do it. Let's do it the easy way for now. I'm going to go into track mode, and then you'll notice that when I window stuff, only the tracks get selected. Then I can press delete to get rid of all of those tracks. Okay, boink, gone. All right. The reason it was giving me trouble is because I locked this component, but we'll deal with that later. And of course, should you make a mistake, Control Z brings it back. Make sure that you save at some logical point so you can bring them back and forth. Now you'll notice that my background, I don't have the grid. So G will toggle your grid. I find it just looks a little bit nicer for the videos to not have it. But usually when I'm laying parts out, I do have my grid turned on. It's just a personal preference thing. All right. Okay, so take a few minutes. Place your components similar to this. They don't need to be exact. As a matter of fact, you can add your own little bit of flair at this point if you wish. But do keep in mind that we wanted to do things like keep this capacitor as close to the microprocessor as possible. You definitely want the programming port and the reset jumper in a logical place, and try to lay out your parts so that the flow kind of makes sense. You can see we come across here through our diodes and then straight down to our transistor, which is then our base comes in a logical fashion. The idea is that everything kind of flows in a conventional way. Okay. So once you're done, the next thing is that we want to go in and we want to add a wire label. And so I mentioned that we deleted the ground from our power supply. What we need to do now is we need to actually add a wire label. Okay, so in this case, we're going to call it ground, and it means that the wire is going to act like a conventional ground. And so just play along here. And the other one that we want to do is we want to create a new net class called AC. So what is a net class? A net class is a set of rules that apply to the wires. And in this case, we're going to modify the net class so that it has bigger traces to handle the AC current should there ever be a short or a problem. Okay? And so what you're going to do is under wire labels, you're going to say create a new, and then type in AC and press OK. And we're not going to worry about changing it just yet, but know that it is there. Okay. And so what we've done here is we've set our class equals power down here, AC up here, and any place that high current is going to be traveling. So high current AC, right, and high current DC. And you'll notice that this one probably isn't necessary, but we do want high current here. And we've gotten rid of this, right? And here, all the way up to our real power, which is over here. And we also want to set this as class equals power down here. Oops. Class equals power down here because we're going to rename this later. All right. Okay, so when we go back to our PCB layout, we can go to our design rule manager, which is up here in the top right hand corner, and you're going to change the trace style. In this case, you want to change it to T12 for the power, and when you change over to AC, you want to set it to T20. And so T12 and T20 is referring to the thickness of the trace. So 12 thousandths of an inch or 20 thousandths of an inch. So 0.02 of an inch, it may not seem that big, but compared to the conventional 8 thou or 6 thou, it's quite beefy and can carry a fair bit of current. Okay, next, we want to actually lay in a ground plane. Okay, so here we are. We've got this. Why don't I create the actual what we're doing? Okay. Okay, so there we go. I've laid my circuit out. And the next thing that we want to do is we're going to go under design, and I want to do a power plane. Okay. And in this case, we're going to be set to the bottom copper, and I'm going to choose a net. In this case, I'm going to connect it to the ground, and I'll say, okay. And that's fantastic. Okay. We're all set. We're all set. And previously we deleted this. And so we have all of our connections, except I don't have my jumpers. Okay, so next we're going to talk about the auto router. And let's take a look at what happens when we just press auto route. So there's a couple things to point out. You'll notice that your AC signals wires are heavier, right? They're nice and beefy, and you have fairly large, so T12 traces here that run throughout all of your power. And then your signal stuff is a little bit smaller. It's like T8. It might be a little bit hard to see with the naked eye just looking at it, but it is smaller. And you can imagine that as you got more and more complicated designs, this would actually be a very helpful tool so that you don't end up missing the odd trace here and there. It kind of gives you two opportunities to make sure that your traces are going to be strong enough. Notice though that it's sloppy. I mean, no auto router does a perfect job. But I mean, silly things like why would Proteus want to do this, right? I mean, you're already here. Why not go through the pin? And part of it is, I'd like to give it credit and say that, he wants to do a star point for the power. It doesn't want to run the power across a pin, which is a really bad idea to start with, but I don't know that it's that smart. But yeah, speaking of why you wouldn't want the ground to go through a pin, if something ever happens to this pin, or you do have a lot of current running through it, it will heat that point up. Or if you were to be removing that chip, you could damage it and end up with a problem. So star points are a good idea. The star point is where the power basically comes in and then branches off into multiple places. And so what's our best plan here? The best plan is to make sure that important traces are laid down primarily by hand, and then you can run Autotrace on things that you don't really care about. And we'll circle back to that later. All right. The next thing is if you actually click on the 3D icon, you should get a view that looks similar to this. And so here's our input and our output. We've got our power LED. We've got our nice diodes. We've got our bulk capacitors, our pass transistor, our regulator. We've got 3 diodes, 3 resistors, transistor, the base, okay, a microprocessor. It looks pretty good, right? And so this is in essence what we're doing for our in-class exercise. Now for your homework, I do want you to clean up the PCB. I want you to finish it off and basically run the schematic simulation. I want to see an oscilloscope capture of the PWM signal running. So that's fantastic. And it's a screen capture, so you don't need to send me the whole file. Just print me the PCB and do a screen capture, drop it into a PDF, and upload it. And as a bonus, what happens on your computer as you switch the LEDs and resistors from analog to digital? Can you actually get it to show the fading, which would be fantastic. Now, this is a 2-week assignment because next week is your test number 1. Next week is test number 1. And very similar to our previous class, we're going to have a practical portion, but unlike previous classes, we're not going to have the quiz portion. And so the best way to study for this class is to actually do your homework and be ready to design a very simple circuit that's similar to what we've done so far. Okay, so to date, we've been working on PCB layouts and schematic capture and a small simulation. And so be prepared to create something that you should be familiar with. All right. Okay, so that's it in a nutshell for our lecture this week. If you have any questions, comments, suggestions, please feel free to email me right away. I'll respond to you as quickly as possible. And hopefully you're starting to enjoy Proteus and really see the power that this software package can provide us. All right. Have yourself a great week and have fun. All right. Bye now.